Awesome. Welcome, everyone. Really glad to be here. We took a quick break, about a month and a half, short break. Some of us traveled in Europe, specifically me. I was visiting my home country, Albania, and I have family in Greece as well. I hope you got to travel a little bit as well, do something new during summer 2021. But while we were traveling, we also got to work on a cool project, and it's our pleasure to share that with you tonight. So my name is George, and I'm joined by my great friends from all around the country and my great co-hosts, David and Robert. And I really want to thank everyone for joining us tonight. If you're watching us from YouTube, welcome again. This is another fun session. Hopefully you can join us online live in one of our events. I know that some of you have completely different time zones, so I respect that. If not, looking forward to our next event together. Cool. Yeah, I love the chat. Okay, I will get starting. Robert and David, do you want to say anything before we start? Cool. Welcome, Kathleen.
I'll just say welcome to everybody, and we're really glad to have everybody back. And I think tonight's going to be really interesting. So stick around.
Yeah, great to see you all again.
Awesome. Cool. All right, friends, let's get started. So who are we and what do we do? Our community is called Deep Learning Adventures. We do a lot of cool events, including deep learning applications. We've done computer vision applications in the past. We've done NLP applications, structured data, time series, and so forth. From time to time, we also invite great hosts, and more on that to come at the end of this session. We're happy hours. Basically, we have a really cool community, and thank you everyone for joining us tonight and making this a really good place and a really good community to be part of. So all the links that we're going to need for tonight are in the meetup page, and I can share that with you. And, if you're joining us from YouTube, that will also be in the recording. But basically what we'll cover today is this cool project, and we'll talk about it in a second. Again, I want to make sure that all the links, I'll share them in the chat, but if you go to the meetup page, you have a link for the presentation, as well as all the material you're going to see today. So we have a lot of material. We just put them up on a Google Drive. We share that with you. We want to make sure that you have all the resources so you can experiment or use that as a reference for your own applications. And last but not least, you can join us on Slack. We have a link here. I'll share that in the chat as well. And you can also find all the recordings on our data and deployment playlist. We have multiple playlists. This is the latest one. As you've seen, we've covered the specialization from Coursera using different platforms of TensorFlow, deploying models in the browser, on devices, using some cool applications of data pipelines, as well as some advanced applications of them. And at the end, we did a get-together, which was really fun with my co-hosts. And as you'll see, that was a key ingredient for this session. Cool. The presentation again is on there. Let me just make sure I share with you the links in case you want to access them later on. Great. Cool. So, phase detection problem. Why did we pick this project and why are we here tonight? So, as I mentioned, I think beginning of August 2nd to be specific here, we were able to get together, really enjoyed it. And really, we got thinking in the end of each specialization, we usually do some kind of a capstone project or a hands-on project. And we hadn't done that for a while. So after doing this data and deployment specialization, we're thinking, what kind of cool project would we do so that we would show community the skills that we learn and also have some fun and enjoy collaborating as a team together. I was also abroad. I was in Albania and Greece for a month and a half. So that was a time zone difference for us. And that was also a challenge for us to make sure that we work on this project together. We had some ideas. We were thinking maybe, actually while we were at Lincoln Memorial, the National Mall, maybe we can do some kind of model that counts how many people are in a space. So you need to do some kind of like person detection and then count. Maybe you can count by different categories, or maybe if you want to count, let's say not people, but like maybe cars or buses, things like that. And then we're thinking maybe something simpler. We've seen object detection before. We haven't done a project on it. But what would be cool is to customize that object detection. So instead of just recognizing, for example, faces, which there are a lot of models out there that can do that, it would be cool if we could customize it, maybe recognize our faces. So this is, Robert, this is George, this is David. And that was, the get together was basically the motivation for this project. And we did a bit of research. There were similar projects out there for completely different data sets. We started, the closest one that we can find was this salad detector. Sounds funny, but it's an actual application. So at the TensorFlow tutorial page, if you go, there's a step-by-step instruction on how to build this salad detector. And what it is basically custom images of food and annotated by this, I think 4 or 5 different classes of cheese, tomato, baked goods, salad, and so forth. So there was something analogous to what we were looking for, and that was a good starting point for us. How did we organize our team, and how did we manage to collaborate? So I want to make sure that we could work independently. So once we figure out the scope, the number one step that we had to do was basically data collection and annotation. So we were able to collaborate through, I think we met twice a week, right, Robert and David? Yeah. Early morning for you guys, midday for me, back in Greece and Albania. So really appreciate your availability there. And basically we had a giant to-do list, and we had a step-by-step instruction of what to do, where to put the data, how to annotate them, and so forth. So we had clearly well-written instructions. That's on the to-do list. And then on the data collection part, we have this face images folder here that we could independently collect data and place them there. As you'll see, this model uses a CSV file for telling where an object is in an image, but I'll get that in a second. And then what else? Yeah, some useful resources and links. This train a salad detector was our starting point. And from that, we just started collecting data and annotating them. So yeah, more a little bit on that data collection labeling. So we had a lot of images on our own. We also took some images during our Zoom calls. We wanted to make sure that we had images where both individually were present, but also when 2 of us or 3 of us were present, as well as us with other people in the background. So we had a lot of images. We also collected a lot of new images as well. And we used this cool application or website called makesense.ai. I highly encourage you to check it out. It's very easy. You can upload your own images. And basically you just define your classes. In these classes, in our case, we just had 3 classes, our names. And you draw bounding boxes around your objects, in this case, our faces. So we did that independently. As you can see here, we had some screenshots as well from our Zoom meetings. We want to make sure that we had, representative data set. We tried different variations, looking directly, looking left, right, wearing masks, wearing sunglasses, wearing eyeglasses, and so forth. So we want to make sure we give a variety to the model. So here are some metrics. As you can see, we don't have tons of data, and you'll see that soon that this is not necessarily an impediment. So from Robert, just him, he had about 30 images, 35 images. Him and me or David or the 3 of us, about 20. David had a little bit more, and I had a bit more as well. I had a lot from our group photos. I basically went on our YouTube recordings and took some screenshots from there, as well as on our live sessions. We dedicated like 5 minutes each time we met to just grab some screenshots and annotate them later. So once you use this tool, you have the option to export in different formats. Sorry, I'll open the channel in a second for any questions. So you have the option to export them in different formats, like YOLO format, XML format. We just picked the simplest one, which is a single CSV file. And here on the lower left, you can see how that looks like. So the set is something we introduced, the training test validation, but the tool gives you the path, the full path of the image. This was on Google Drive. The label that we annotated it with. That's the process version. The tool gives you the lowest one here. So you have a label, an anchor X and anchor Y. Where's the XY anchor for each box? The width of the anchor of the box, the height of the box, what is the image name, and what is the total width of the image, and what is the total height of the image. So basically, where is the XY left corner of an image, anchor X and Y, and how wide and how tall is the bounding box. And each row is a bounding box. So one image could have multiple bounding boxes. In this case here, this image, group 26 JPEG, would have 3 records in our CSV file because there are 3 objects that we're interested in: George, Robert, and David. The model, looking at the model, needs data in a slightly different format. So first of all, we need to add the set, training, test, and validation. Second of all, it needs the full path, not just the image name. The full path where this is on Google Google Drive, the label which exists, and then it needs what is called relative anchor points. So it needs where's the upper left anchor point and where's the lower right anchor point relative to the image, meaning they can go between 0 and 1 if it's all the way to the upper left or all the way to the lower right. So now these numbers are between 0 and 1. You just basically divide by the width and the height for the upper left anchor, and you add the width and the height for the lower anchor. There are, you'll see 2 columns that are missing here. There's also 2 columns missing on the upper end, on the end. That's because you can specify each individual anchor, right? You can specify the first anchor point, lower, upper left, upper right, lower left. In this case, we just specify the diagonal ones. We didn't have to specify all of them. I'll pause here. I want to make sure that you've got the data collection and labeling right. Questions, feel free to chat or unmute yourself. I'm not monitoring chat. Okay. Cool. No questions.
So back to that previous slide, we have the word data leakage in the title. Did you want to talk about that here?
Yeah, thank you. Yeah, I forgot about that. Yeah. So how did we assign a training, test, and validation? There are 2 ways to do this. One is, a little bit naive. You just do randomly. You do pick a percentage. Let's say I want 60% of my data to be training, 20% to be validation, 20% to be test. I think that's the ratio we picked. Also keeping in mind that to avoid some kind of data leakage, like the same image or very similar image should not be in the train and test set. I have an example here. You can see me a little bit zoomed out, and I have similar images where it's more zoomed in, but I'm looking in different directions. So one could argue that those are very similar images. And it's me just looking in different directions, or the photo zoomed at different parts of my body. So I specifically did not want to go through the process of basically assigning each location or each background to one training or test or validation set. So I think I followed the approach where 2 or 3 images I set them as training, and then the next is validation, and the next is test. So this means that there might be, or there is there is a good chance that we might have not exactly the same image, but visually to us humans appearing similar images in training and validation, or training and test, or validation and test. Again, I don't know if anybody's worked on object detection projects before, this was our first effort, but if you have any good ideas how to do this without spending a lot of obviously manual effort, please let me know. The other thing I was thinking of is maybe you pass all these images through some kind of like feature detector, and then you identify which images look very similar, and then those images you place them on different sets. But I don't know if that's a good idea or if there are better ways to do things. To me, that was just a way.
Well, there's some pre-processing that really helps visual recognition, and one of them is image segmentation. Coming up with metrics and a labeling algorithm that would be able to draw that bounding box around your head based on its similarity to things that are head-like at different orientations. That way you clip out almost all the rest of the image and have a lot less noise when you actually try to classify.
So you're saying you do segmentation first,
Yeah.
and you identify images that are almost the same based on like the pose of.
Yeah, and they could be templates, they could be kernels, they could be chained kernels, but if you can come up with a simple heuristic, and the kind of keyword is simple, then you can cut out them having to try figure out whether your fist there in the picture is a face that's kind of elongated, or what the hell that half a TV is in the background, etc. So you can kind of cut out the noise. You can concentrate on the signal.
Cool.
It's one of the kind of prevailing theories, at least back when I was in grad school, of visual perception, is that there's a not quite a spotlight, but a way of focusing processing resources on a certain segment in the pixel image, which would be your face there, and then the rest of it is kind of damped out, and the resources are brought to bear on that. And you, depending on who you talk to or what papers you read, you could wind up where people are positing that it's being scaled to +1, -1 normalized rectangle to work with. And there are other people that pay a lot of attention to using hexagonal or exceptional fields instead of the sort of 9-element path that we're all used to, just because the receptors in your eye are actually have a circular receptive field. And so a hexagon is a better approximation. So there's pre-processing can make a big difference in the eventual recognition task.
Cool.
It's sort of like the tomato leaf data set that everybody's familiar with. If you actually have tomatoes, like I did, and I will again, what you want to be able to do is to recognize what might be going on with the tomato leaf, omitting all the stuff that might be around it, hummingbirds and bees and whatnot, or even the background of the ground and whatever your planting medium is. Just kind of focus on the leaf and cut out the rest of it, and then the recognition task becomes more reliable and simpler.
Got it. Okay, cool. Thanks, Chris. David, you're muted.
So I'm going to go ahead and share my screen. That's not the right screen. Where did it go?
We can see your screen.
What screen do you see?
The presentation.
Oh, okay, great. Sorry, okay. If I can get this thing to get out of the way. Trying to go to another page here.
On the upper right.
George, a question before. Did you do any distortions to the images to, like blur them or twist them or anything, or reflect them to increase the size of your data set?
No, I just tried doing capturing to maybe like look in different directions, like wear sunglasses or like do similar things. But no, I did not rotate them, or like usually we do for other image classification tasks.
Mm-hmm.
I'm having trouble getting the zoom control thing out of the way. Do you remember how to do that, Robert?
If you move your mouse, you should see the bar, and you just drag it wherever you want.
Let me stop this share for a second.
My very low tech solution to this in the past has just been to make the browser window a little smaller.
Yeah.
I think I might have to do that just real quick. Okay.
I can share if you want me to.
I've got it now.
Okay, perfect.
Okay. So if you've done object detection, you know, there's many models out there, from the YOLO models all the way through a whole bunch of different ones. And you can start from scratch and build that model. Here, I'm going to show a Keras version of it. And then you've got to do a lot of data manipulation, more than what we've done, to get the data ready for the model the way the model expects it. And then you've got to run a lot of training. And so here's kind of the possible way of doing this. This is a very, very long notebook with many defined things as far as getting the loss right and all the metrics, and then encoding the labels, and eventually down here you get to do some actual training and prediction. So it's huge one, and this has to do with doing the COCO data set that we're used to. So that's kind of the old way. But what I wanted to show was more of the easier way that we decided. We didn't have time to go through and learn how to build our own object detection model. And that really wasn't the goal of this. We were trying to put into place some of the things we learned in the data and deployment course. So we came across, as George mentioned, the salad model, which goes and identifies objects in a salad. And we use that as our kind of our own template for how we did this. And in there, use a neat little tool from TensorFlow called the TensorFLite Model Maker. And let me put this into presentation mode. Here's the URL for it if you're interested in going through and reading it. But it's a library that simplifies the training of a TFLite model with your own custom data. It saves a lot of time by using transfer learning. So you need less data, and you saw that we didn't have a lot of images. So this worked well for us. You need less data to train with and a lot shorter time to do that training. It is currently a experimental library that they put out. So, you know, user beware, it could change. I went into the GitHub for the pages that it's built around. And it looks like they released it or started releasing it, making it public in April of 2021. So it is very new. And here's the GitHub if you want to go look at the actual models. It supports different tasks, including image classification. And as I mentioned, it does transfer learning. So you've got built-in models that are available for you to use, and you can choose one. For image classification, it uses EfficientNet, or you can choose MobileNet or ResNet 50. For object detection, which we're of course interested in, they have the EfficientDet model available. And we'll hear a lot more about that after I'm done. Robert's going to introduce that model. For text classification, they used average word detect and as well as BERT when you need more powerful transformer-based text classification. You can do mobile BERT Q&A for Q&A types of tasks. For audio, they have a browser fast Fourier transform spectrum model, as well as YAMNet, which is another popular audio classification model. And then if you're doing recommendation engines, they have 3 different ones. The first one's the bag of words model. They have an RNN and a CNN. So those are the different types of tasks and models that are available to you currently. And I expect they'll probably add more as they develop the API. Here is the actual API that comes with it. What happened there? Sorry, the API has a data generator, a data loader, which saves a lot of time in the pre-processing of the data that you have to do to get your data into a format that the model is expecting. And here we're looking at specifically the API for the object detector, which is what we're interested in. You can generate data sets from CSV files, from TF records, Pascal Vote, which is another popular object detection format, and others, including from cache. Another class in this API is called efficient det spec. This is where you specify which version of the model and all the things around the model that you want to use. You identify the one you want with a string, and here's the 5 strings that are available for efficient det, and Robert will explain the nature of these later on. And then finally, we have the object detector, which is the class that does most of the work for you. It has methods such as create, evaluate, export, evaluate TFLite, and summary. And I'll talk about that on this page. So these are the steps that you would use to use this model maker in your notebook and in your project. There's 7 things to do. The first is you want to choose your model architecture. Some of the ones, of course, have different ones, but here we're just going to give it a specification for efficient det. The next step is to use that data loader class I talked about to load up the data set for you. And you'll see in the collab how these are done, but they're generally like one line of code in your notebook. So it's very simple. The third step is to train the model. That's done with that object detector. You're going to evaluate that model against your test data and see how it's doing. If you're happy with that, you can then do step 5, which is export that model as a TFLite model, which is going to do things such as quantization and things to make the model more efficient on an edge device. Then you can take that TFLite model and evaluate that model also with an evaluation function for the TFLite, because you'll get a change in performance when you've done all those different things to produce a TFLite model. So you want to evaluate, make sure it's still working against your test data the way you expect it. And if you're happy with that, then you can deploy it to your edge device and start using it. So that is the steps that we take, and this is a very nice for developing TFLite models. It's a very useful library. It's very efficient, and we'll see that in just a minute in a collab. Any questions before we talk about the efficient det? I'll let you go. Okay.
Thank you, David. Yep. You'll see the simplicity. So intriguing. When you're scrolling down that RedNet example, I was like, okay, where do I start and where do I begin? I don't see any questions. Cool. Robert, do you mind sharing your screen?
Okay, let's do this.
All right. Thank you.
You can see my screen now?
Yes.
Yes.
Okay. So I believe I am now the last thing standing between you and the results. So let's not belabor the paper too much here. But a few points of interest. Let me see if I can make this a little bigger.
You can hit on slideshow on the upper right.
Yeah. So efficient det is not a model, but a family of models, as David mentioned earlier. It came out of research published by Google Research Brain Team in late 2019, fall of 2019. And it actually is very much inspired by the very similarly named efficient net. The difference here is that efficient net is a image classification model trained on ImageNet, and efficient det borrows a lot of the same ideas and applies them to the object detection problem. So remember that the image classification problem is simply you take an image and you output a discrete output. The class of whichever of a number of classes have been predefined. You have to select one of them and say this image is that class. Or it could be a background class. I think ImageNet has 1,000 classes overall, one of which is background. Hey, it's none of these things. But the other 999 are distinct types of objects, animals, vehicles, plants, etc. Efficient Det uses a very similar architecture to EfficientNet, but as it's a detector, there's a few extra things needed. For one, you are not only outputting classifications, so in our case, whether this photo contains George, David, or Robert, but you also want to be able to draw a bounding box. So you actually have 5 outputs for a given detection. The identification of who it is one, and the 4 coordinates of the bounding box are another. So a couple of things about efficient Det. One of the aspects of the design that was important was to make it a 1-stage rather than 2-stage detectors. And if you're familiar with some of the other famous convolutional neural nets, you have some of the really fast networks that can be implemented in mobile devices are 1-stage detectors. This is the family of YOLO, SSD, etc. And there exist some other algorithms that are maybe a little better in performance, but slower because they're 2 stages, where you have one neural network that is predicting that is choosing which of a number of anchor boxes might contain something, and then another network that is doing the image detection around that proposed location. So in this case, we want a 1-stage detector because we need it to be fast. Another aspect of the efficient Det, as we mentioned before, I'm going to skip to this 3rd bullet here. It's designed a little bit like EfficientNet, and we'll see that in the next chart, but in the sense that it uses an EfficientNet backbone. So the convolutions are designed like EfficientNet, and then what it does is it uses a bidirectional feature pyramid network, which essentially is taking, so you have, let's jump forward to the next slide. Anyone remember the keyboard shortcut for next slide in Mac? Can't find it.
Vacation was too long. Just click anywhere on the image, on the slide.
There we go. And that, okay, mouse up and back. There we go. Cool. So the backbone is shown on the right or the left. It starts with some number of, or some size resolution, and typically what happens at each convolutional block is the image will get smaller and smaller and smaller. And this is through some kind of strided convolutions or pooling layers or a combination of both. Typically you have a factor of 2 drop from each layer. And what the efficient Det is doing is it's taking layers 3 through 7 and taking features. So each of these little dots here, they're drawn a little bit like single nodes in a neural network, but they really have a width to them as well. You can think of them as being all the channel outputs for each of these layers. And then you get this thing to the right here, which is, what it's really doing is it's combining features that can be detected at different scales. So if you want to detect a person's face and maybe recognize the individual, you're going to want to use features such as the overall shape of the head maybe. And that might be a larger scale feature that's detectable over here, I'm sorry, out here. And the smaller scale features, the individual edges that might form things like eyebrows, nose, etc., those are going to be at a different level, which is going to be best at detecting those at a different level of resolution. So what you want to do at the end of the day is to have some kind of network that can combine the information from the features that are best detected at each of these levels. And the bidirectional feature pyramid network here is an attempt to learn weights to do this in a few layers that are added to the right side of this network here. And this is processed here before being fed into the class prediction net and the bounding box prediction net. So there were a couple of alternatives considered here. The feature pyramid network that this was inspired by was another publication that had been 2 years previous. I think that might have been Facebook. I can't recall though. And then we have PA net here, which just adds the reverse connections as well. The first one only had features being fed down the network. And then you have this neural architecture search inspired feature pyramid network, which is really just a way of saying we could have blocks anywhere. Let's do a massive architecture search to figure out which ones seem to work the best for the data. And this is one example that may result from such an operation. So with the bidirectional feature pyramid network, what they've done is they have said, we're going to take what works here with PANet. This one, the neural architecture search, is way too slow and doesn't provide enough benefit over these other methods. They wanted to get rid of blocks that only had one input feeding into them, hence they get rid of the top and bottom layers, combine these ones together, and then just learn weights for this shape of block.
Sorry, can you repeat that? Top and bottom layers? What did you remove?
So if you look at the PA net and compare it
Oh, I
to
see.
by FPN,
Hmm.
what they've done is they've removed a block here, or a cell there, and they have basically removed this. They've removed this one too, which actually does have two inputs, but this one has one input, so it's kind of topologically the same as
Oh, I
removing
see.
this one and then just shifting that one over.
Got it.
So one thing that David mentioned earlier is that there are multiple different sizes of the efficient det, and that's true of the efficient net as well, and that's part of the reason that they borrowed from this efficient net model for the efficient det. And here the idea is that for different use cases, you might have a different requirement as far as power budget, number of pixels, resolution, or performance. So it's useful to define a family of models that you can select the one that performs at the level that you want given whatever size, weight, power considerations are required. So that is very relevant when you're talking about using these networks on mobile phones. And in our case here, we're using the efficient det D2, which is this one over here. So performance comparable to some of these other ResNet, neural architecture search, FPN, this one, but at far lower floating point operations. So what the efficient det and the efficient net do is they define this family of models that really only have one parameter that is used to scale the depth, width, and resolution altogether. And the efficient net paper, which is linked here, archive 1905, so spring of 2019, was published by the same team at Google Brain for the image classification task. And there they did an extensive search for what sort of functions would be useful with a single parameter scaling. So both of these papers talk a little bit about that. Some of the decisions in the papers may look a little bit arbitrary. It's not. It's clear that there's been a lot of tuning going into the design of the models in order to get them to fit this single parameter compound scaling idea. But it, at least once you've done that definition, it defines this family of models here. One thing of note for anybody who wants to look at the paper here, and if you're looking very carefully at this chart here, you'll see that the performance quoted here in the figure, 55.1 average precision, is actually not even on this chart at all, which confused me while I was reading the paper. But it turns out that that's just a tweak to the D7 model that adds a number of more parameters and basically would extend the curve up here without adding another layer to the backbone, which would then presumably have been called D8.
Cool. Really interesting architecture.
So let me just, I'll show that these figures all came from this paper here, Efficient Det, Scalable and Efficient Object Detection, Google Research Brain Team, and the other original paper on Efficient Net for image classification is also by Mingxing Tang and Kwok Li, also at Google Brain, and this is where they did a search for the design of that compound feature scaling. This is a very quick overview of something that's obviously more complicated to discuss here very quickly. Any questions right now before we go on to the main event?
There's nothing in chat. So.
I have a quick question. Has anybody tried to get the access to the code and run it, or just curious?
So the code is available. I believe if you go to the paper itself there, it will give a link to the GitHub site.
Yeah.
I have not played with the code. I don't know that anyone on our team has outside of the model maker and TFLite.
Yeah. Okay. I was just curious.
Awesome. Thank you, Robert. I just joined from my phone. That's why you see me twice on Zoom. Yeah, that was interesting architecture. I like that it combines features from different resolutions, right? From the really original image to like an upscale version of it or a downscale version of it. So you're looking at large objects or smaller objects based on where you're in the resolution pyramid. So that was an interesting approach.
I don't know how applicable that is for human detection as compared to some other objects. Certainly if you're trying to distinguish two cars or military tanks or something, you might need to have really huge differences in resolution. For people, maybe there's some, but probably at a smaller scale.
Right.
I just wanted to chime in real quick. The reason why I personally had some interest in this is I have a personal project that I'm trying to that I'm pondering working on, and basically the application is a kid's soccer game, and I want to basically build an app for an iPhone that I can hand out to all the parents, and just have the iPhone set up and prop it up in a soccer game, and then have this app basically do object detection on the soccer ball and follow the ball the entire game. And so I'm that's why I have an interest in this, because it kind of could apply to that application, and I thought I'd just throw it out there. Maybe it's a dumb idea, but or it's overkill, but that's that. Yeah.
There's a video out there of a model they used it for actual broadcast cameras that were broadcasting soccer. They did the same concept. It was going to follow the ball.
Yeah.
And it worked very well until they had a referee that was bald, and it began following him instead of the ball. So it failed pretty well. It's probably on YouTube. I'll try to find it. But
Yeah.
you shouldn't have that problem in a child's game, but you know.
Well, I mean, just to give you, so the motivation is that there's this $3,800 piece of equipment that we're purchasing, right? That does this, but they use lousy cameras inside there when it does the digital zoom, and it zooms out into the distance and tries to, and it has object detection built into it. However, I think there could be a lower cost, more kind of decentralized approach, you know, with all the parents using an app to do this, right? Because we were all carrying amazing cameras in our pockets. Why not repurpose it for that? So anyway, so let's see. Well, I'll see what happens. I'll dig into the paper and research it more. But that's my my goal here.
Cool. Yeah, interesting
Yeah.
application. I thought when you mentioned that you wanted the app to track their kids so they have an idea where they are, because sometimes there's so many kids in the game and they don't even know where their kids are in the game.
But I mean, well, so that is something I've thought about, and you can track their faces, right? But then,
Right.
but this company that we bought this $3,800 piece of equipment, they all wear tracers, which is a GPS module that they insert into the back of their shin or the back of their leg that's strapped onto them, and it tracks their GPS location the entire game. And so it'd be nice to take that extra accessory out, but the problem is that GPS thing gives them extra analytics of like their running speed and their location, how much time they're running, how many miles they've run, and all those metrics. And I'm not sure an object detection system could totally do that, but you know, without having to you know, circumvent the sensors on in each individual player. But that's how they were that's how they solved the problem. So, but I'm trying to find a lower cost solution. So anyways.
One of the great things about this space is that you really don't have to get into the weeds reading research papers to implement solutions, right? We've presented a little bit about the paper here just for interest, but so much of this stuff has been implemented in tools like the Model Maker, where you really can stand on others' shoulders to do the last step for your own project.
Yeah, I'll look into that Model Maker. Is that I must have missed that. Was that part of your presentation? I came in a little bit late.
Yeah,
Okay.
and know that we record all the presentations as well, so you'll be able
Okay.
to find this on YouTube.
Okay.
Too.
Cool. Thank you. Thank you.
Cool. All right, I just want to give us a quick demo of the app before I actually take a deeper dive into the Colab and the code and unfortunately lose or not lose somebody. So I want to make sure that we have something to look forward to. So I joined from my phone as well. That's why I'm twice on the grid here. And let me share my screen. Start now. Let's go to the app. So this is the app. We didn't build it. We used the boilerplate app that the Salad Maker tutorial had. And it's a very basic app. We've seen similar ones from our other project as well, from the specialization for both image classification as well as object detection. So it has two features. One is you can have predefined images, as you can see here at the bottom. And I uploaded some predefined images for us. And the other one is you can take photos of anything, and it will run the model on the image that is captured from the camera. So let's try the preset images first. This is one of the images that we have. And as you can see, it's pretty, I mean, straightforward, not straightforward, but pretty quick. It's able to identify our faces correctly with different degrees of confidence. Let's click on the next one. This is where our faces are a little bit smaller. So David is 77% confident, George 74, Robert 78. This is during a Zoom call that we had during the summer. You can see we're looking pretty straightforward here. I mean straight. And this is, we're trying to fool the model here, but he got us using sunglasses or eyeglasses. And another thing that I'll talk in the end, during one of our Zoom calls, I think specifically with me and Robert, it was just the two of us. So we had these very long looking images, and the aspect ratio here was in such a way that it took me a while to understand what's going on, but for some reason this aspect ratio, or this width and height ratio, the pre-processing part of the model could not handle it properly. So we have a few images that are this ratio, and they are not, the model could not basically pre-process them and run the model on them. But if I take a photo of this photo from my app, as you'll see in a second, it will detect it properly. So that's the one feature part. At this point, I'd like to take a photo of us, but hold on, how do I do that while sharing my screen? So I'll take a photo of us. I'm sharing my screen, so our images are very small. Let's see if this will work. So take photo. You can see this is our call. So I'm going to zoom in on us. Let's see if this works. So take photo. Yes. Okay. So Robert, 68. Oh, it misconfused David as me. George, 51. George, can anybody see that? What is it? 83. The right way to do this is if I stop sharing. So let me do that.
I think it's just David's lucky day.
But there's also the interesting question of leakage here, like given that it's printing our names right below us too.
Oh, interesting. Hold on. That is a good point, because when I took screenshots, I specifically hid the name. So Zoom question of the day: how do I hide the names?
I don't think you could have learned it if none of the training had.
Yeah, we scrubbed it from the training data.
We should be okay.
We did. But how do I remove it now, though?
I don't think you need to. I mean, it's not going to know. It's not trained on letters. It won't know our names that way. There's no leakage there.
Sure. We're just trying to be extra. Okay, let's try it again. So this time I will take the photo with my model, and then I'll share my screen. Okay. All right. Let's do it again. Okay. Let me share my screen. Okay, great. So you see the image is a little bit bigger. All right. Robert 62, David 63. I can't even see what it says. George 74, 70 something. Can I zoom in?
Also, notice that it ignored Kieran. Didn't identify him as one of us. So
if anybody's brave enough to come off camera, we can take another photo and see if it detects one of you as us, which it should not. But yeah,
That would be my unlucky day.
No, not at all. So I'll stop sharing. Yeah, and let me run it on some of our images as well. So we have a bunch of images. Let me actually share my screen with you guys so you can see what I'm doing. So under our folder, we have these face images, and we have the folders for each one of us. I'll go to mine. So usually the individual ones are on their own. We have some group ones. Yeah, let me pick some group ones. Group ones, maybe. Oh yeah, so this is the one that didn't work, right? Remember the aspect ratio, so I'm going to zoom in a little bit. I'm going to take this with a mask. It's going to be tricky. Let me take a photo. Just taking a photo here. Okay, and then share screen. Oh, sorry, I need to stop sharing. Share screen. Okay. So that's the photo of the long image that we took. Look at that. Robert 80, George 78. Cool.
There we go.
Cool. Let me take another photo of a group photo. Oh, this is a good one. This is when we had Lawrence with us. Okay, let's do this. This is going to be a tricky one. The lightning is a bit weird here. All right, look at that.
That'll be a good one to show Lawrence.
Exactly. Let's pick tricky one. What is a tricky one? The trickiest one, from what I understood, is when the faces are very, very, very small. So I have a tricky one for you guys here. I doubt this will work, but let's push the model to the edge. This is when I was going to that cashless store that uses computer vision to check you out. So as you can see, I'm a little bit blurry here, the three of us, and I'm here on the main screen, so it should definitely pick me, but let's see if it picks anybody on the lower upper right. Okay, it picked me as well, with 50-something% confidence. And let's try a last one. Let's try one.
Is there a cutoff for the display? Like it'll only display it if the confidence is over 50% or something?
Yeah, you can set it up, yeah, to only display images or results where the confidence level is above the threshold, and you can configure that, yeah. Okay. I'm trying to find a tricky one. Okay, maybe maybe this one. This is not really a tricky one, but let's see. Okay, so it picked George and Robert 70-something%. Let me see if I can come closer. Say here. All right, there you go, David. I'm gonna leave you behind. Okay, so 89, 76, David is 64. Okay.
I exist.
Yeah, I don't know, maybe the illumination or maybe the light that I have here next to me. Then yeah, I have some more. I'll share with you in Colab some more examples so that we can comment on that. Cool. That was the demo. I will give the meeting from my phone. So yeah, that was a cool, neat demo. Any questions about the demo before we get to see how we actually train this model and how do we deploy it? Cool. Okay. So yeah, so Robert talked about the algorithm, the model. This is let me make this bigger. This is the layout of the demo, as you saw. So you have a preset images, as well as you can have the option to take photos. Okay, let's jump real quick to the Colab. I'll make the font bigger. Is good. Yeah. So the link of the event, the link of the recording, you can contact us on LinkedIn as well if you're watching this online. This is the Colab, the tutorial that we're inspired by, the salad detector, and this is a screenshot from that salad detector. So I'm not gonna go into full details. I'm just gonna give you basically the basic ideas of how we structure this. So number one is getting the data, and we followed the Google Drive format. So here are some commands to just mount my local drive on this Colab. You'll have to go through the authentication. You'll generate a unique code for you. You'll enter it here and basically have access to your entire Google Drive. We have a specific path. We have a shared folder that we share, the three of us. That's where all our data lives. And we have a labeled CSV format. And you'll see how that looks like in a second. So the path is there. A little bit more about the model maker that David mentioned. Prerequisites, what libraries we're going to need. We're going to need TensorFlow, and specifically we're going to need TensorFlow, a specific version 2.5. And we're going to need the model maker library, and some Cocoa tools as well for manipulating images and bounding boxes. When we started doing this project, everything was working fine. But then TensorFlow got updated, right, David, to 2.6, number one. Number two, I think the TensorFlow team released a new version of TFLite Model Maker. So for some reason, everything was working fine for us, except for model TFLite Evaluate, which is the very last step of the notebook. And by then, the only thing we had changed is add more data. So it took me a few days to figure out why is more data breaking my model. This doesn't make any sense. The only thing I could think of is maybe doing quantization. It's picking up some kind of representative set that the new data is breaking. It's like outside what it was trained. Like I wasn't sure. So I was removing data, but then I realized it was not data related. It was TF version related, as well as this use deprecated legacy resolver related. So caution to that. The tutorial was updated, so that was a good thing. So I realized, okay, this is what you're actually using, because a few days earlier, this was not the exact command. It was just TensorFlow, and it didn't have this flag. Cool. NumPy and operating system for just accessing some files. And then from Model Maker, we're gonna use what is called this model spec, where we specify which specifically model we want to use. This is like a config file. And the object detector main library that David covered. So yeah, we use 2.5, and then these are just plotting libraries. So we have some pandas. We're going to capture our data, seaborn, pyplot, and some random for just picking up random images for detection. Some image processing modules, IO, PIL, and CV2, and some utilities for timing how long things take and where our files are. Cool. So this is an example of the CSV format. Zoom in a little bit more. So the set, the full location of an image, the label, the normalized first anchor, upper left, missing, normalized lower right anchor. Cool. You can also use, if your data is in Google storage, GC, you can do that. If it's local, you can do that as well. And we use the local path. Let me zoom in a little bit more. Here we have the family of efficient depth models that Robert covered. They vary in size and latency. So the smaller it is in size, the smaller the latency. But then again, the average precision, I think this was based on the Cocoa data set, yeah, is lower. And all the way to the bigger one where the size is 5 times, the latency is 7, 8 times bigger, and the precision is 2x. So pick and choose. For our model, I think we went somewhere in the middle in this TFLite 2. And I just wanted to share with you that these models are also available on TF Hub. I'm going to switch tabs just for a second. So they're also available on TF Hub. Yeah, sorry about the contrast there. Cool. So yeah, so model spec get efficient light 2, and we get this specification, which is basically an object that points to our efficient depth 2 model from that family. Then how do we read the data from the CSV, figure out which belongs to the training set, validation set, test set? how do we bring them locally, and all that. This is just one command with this model maker. So you just do object detector data loader from CSV. You give it the path, and that path, remember, was in this very specific format, right? The file was in this format that I showed before. I realized during this project that PNG images, screenshot basically, were not a good idea, and for some reason this model couldn't handle them, so I had to convert them to JPEG. This is just a code to show the image extension of an image and iterate over them and make sure that I don't have any PNG. Okay, in terms of data, we have 155 in the training set, 50, just 60% of them, 20% of them are 50 in the validation set, and 45 of them in the test set. Okay. We're going to use a batch size of 8. We'll process 8 images at a time. There are 2 options when you train the network. This is the training part. You can train just the very last few layers, or you can train the entire network. Again, I experimented with both. As you expect, this train whole model true give us better accuracy, but at the expense of longer training times. Specify the validation data, batch size. You can also specify the epochs, the model spec, which model you're using, what is the training data. These are the arguments to object detector create, which is basically reading the data, fitting the model. One thing that I didn't see, and maybe this is still experimental, I didn't see a way to maybe do some kind of early stopping or saving the model like we used to doing back in our image classification project. So this epoch equals X was a little bit time consuming, but I'm hoping maybe in the near future I'll have a better solution. Cool. As you can see, it takes a couple of minutes. We have what? We have 155 images divided by 8. We have about 19 steps to go for each epoch. So it takes about, it takes a couple of minutes per epoch basically, and you get a bunch of metrics that we'll take a closer look soon. Number of classes 3. The label map is our labels, and this is the model summary. So you won't be able to see the entire architecture like the pyramid architecture, but it has a keras layer that has basically a collection of all the different layers. And then in the end, as Robert showed, there is a class net that does the classification, the prediction of which class this is, one of the 3, and then a bounding box prediction where exactly for each class is the bounding box, where's the anchors, the 4 anchors. So we have about what, 5 million parameters. We did train whole model true, so most of them will be trainable. And we have about 70K that are not trainable. I was taking a look at the structure of this model. It has a model inside of the model. And I was looking at the loss. Yep, model loss has a box loss, has a IOU, intersection over union loss. It has focal loss, and then it has a sparse categorical cross-entropy loss for classification. So there's 4 different losses here. Optimizer, just standard HDD, I think. Then the history, which is basically all the metrics, all the loss functions. I'm going to scroll down to the actual visualization here. I just kept them there for reference. So we will pivot all our data from this long dictionary to pandas data frame. And this is how things look like. Let me zoom in a little bit more. We have, so each record, each row is an epoch. We have a detection loss. We have a classification loss. We have a box loss. We have something called regularized L2 loss. We have something called loss that, as you'll see, is the sum of, I think, dead loss and reg loss, if I remember correctly. Yeah. We have the learning rate, gradient norm, and then the validation versions of detection, classification, box, regularization and loss. So this is a wide format, and they are in different scales, and it was not easy for me to visualize them. So what I did is I melted them, as this is called in Panda. So basically you unpivot them from wide to narrow format. So, and I also grouped them by the different scales they have. So I think it's easier if I just go to visualization. So I grouped the box loss and the learning rate together because they were similar in scale. As you can see here, epochs is on the x-axis and the loss function and learning rate on the y-axis. So blue is training, orange is validation set. So as you can see, the loss for both of them is dropping and improving, so which is a good thing. Can't tell here if it's overfitting. In other setups, it was easy to see if it was overfitting if basically these two time series diverged. If we look at the regularized loss, and we'll explain quickly here what they mean. They also seem to be converging, stabilizing at a point. And then for the other losses, detection loss, classification loss, they're also, the trend is downtrending. There are some spikes every now and then, probably from the randomness of the data or the batch, but I can see the trend is downward. Did we want to say something about this loss functions or norm, Robert? Is it a good time or? Okay. Then the next step would be to, we have a couple of links here, and we can go maybe after this of what does this metrics mean and how they're calculated. Then the next step would be to run this model on the test data, on data that the model has never seen. And there's a list of categories here, okay? Let me zoom a little bit more. So notice it took only 39 seconds, and the main number we're interested in is this average precision, which is basically taking an average over all the different classes, which we have 3. This 50/75, I think, is using the threshold where the intersection of our box with the true box, the IOU is above 50%, 0.5, so they need to overlap at least 50%. And 75% means that we need to be closer to the ground truth. So we need to be at least 75% overlapping. So basically, the tighter our standards, the lower our precision. Then the average precision over all images classified correctly as David, as George, and as Robert. So it looks like it performed a little bit better on David than me than Robert. And then when you see this APLMS, so these are the average precisions for objects, places, basically bounding boxes where there are other small. Maybe I was sharing my screen and we're at the top banner of Zoom. That's the S. So for the small ones, we didn't do very well. It's very challenging. Medium size, maybe we were like, and there are specific numbers in the link that I'll show in a second. Maybe we were in like 10% or 20% of the image was occupied by our bounding box. A large is where maybe our faces, or one of my face, for example, was the main object of an image. So that's the average precision, large, medium, small. Then we have average recall, large, medium, small as well. And this max 1, 10, 100 is if you only pick one object out of however they're in the image, what is the average recall? If you pick at maximum 10 objects, what is the average recall? And if you pick at maximum 100 objects, what is the average recall? So I just threw a bunch of metrics there. A good website is this Coco. I have a link on the slides as well. But this detection evaluation gives a better explanation of the different metrics and what does this mean to be small, medium, and large, and a good explanation here in terms of pixels. So yeah, I highly encourage you to check this out.
There's another really great explanation of average precision in general at a blog post that I put in the slides or in the collab right above where you were.
Okay, yeah, let me find it.
The Medium post there
Yeah,
is
perfect.
far more detailed, but it really explains how the average precision metric works.
Right. Awesome. Thank you. Yeah, this is the same screenshot that we just showed. Okay. Thank you, Robert.
A little bit more background if the Cocoa descriptions aren't enough for you.
Right. Cool. So then we did this for, just to give you an idea, we did this. So remember this number. If there's only one number to remember, it's 0.53. We had different versions or different stages of this project. In the very beginning, we trained it with just the top layers, just the classification layers basically, and the object and the box detection. So train whole model equals false, and I think it was just me with no group photos. So as you can see, we did pretty bad, 0.08. It just picked me because there were no group photos of us together, and this negative values is probably undefined. Then the same model or the same data set, but with train whole model equals true, a little bit better, 0.13, mine 0.4. So we improved a little bit. I added a few group photos, so 0.25, better, and then it's picking up Robert and David, awesome. Then this is where we added even more images from Robert and David, and we got where we are now. 0.53 and 60s, 50s, and 40s for us. As reference, the salad dataset achieved about 25 average precision, and it was very easy to pick up salads, and it was very hard to pick up baked goods, as you can see, or seafood. Cool. This is just as a reference, so I want to make sure that we are a little bit better or significantly better than this basic dataset. So that is still in the Python world, that is still in the TensorFlow world. Okay, now we want to deploy this.
One thing that's interesting about that those salad numbers there is just look at the huge spread from one item to the next.
Right.
It's it does very well on salad, maybe because salad is a unique type of entity amongst those, while baked goods may be really difficult to distinguish from seafood or cheese.
Yeah.
They kind of maybe have similar colors, while the salad is going to be a totally different texture, more greens.
Right. Plus, salad is usually a collection of things, right? So usually salad, I imagine, would be a larger object, or be easier to detect. Versus tomatoes, which is an ingredient. Seafood is probably an ingredient. Cheese is an ingredient. Baked goods, I don't know why it's not doing bad. It's not doing good. Baked goods are usually larger in size as well.
So for our images, we had much closer numbers, right? The range was from about 0.6 to 0.46.
Yeah. Cool. Any questions about this metrics? Let me know. Okay, so as I mentioned, we're still in the TensorFlow world. What if we want to take this model and deploy it on the edge? We want to deploy it on Raspberry Pi or Android or iOS device. So to do that, we have to export it to a TensorFlow.Lite model. And what that does a lot of things. We've seen this in our specialization as well. So we will do what is called quantization. So we're going to look at the different values that are weights take and our biases. And these are probably high precision floating points. We're going to reduce that expression range from high precision to maybe lower precision. We're going to bin them, basically, quantize them. As well as, instead of detecting, I think the original TF Hub efficient dead model detects up to 100 boxes in an image. We didn't have one where there was 100 of us in an image. The TFLite one detects maximum of 25 detections. So that's another thing. So how do we export?
George, can I ask you to show the on the collab the directory structure? You've run this, right? So it's current.
Yeah, I've run this. Yeah.
In collab on the left side, you can.
All the directories.
Yeah.
Oh, yes. I ran this a while ago, so.
Oh, it may not be. So it may have already deleted. Yeah, that's what I was looking for.
Yeah.
Oh, okay, never mind. I think by default, when you run export, it saves the TFLite model and a standard TensorFlow saved model. And you can also do the HT5. So it's the export command. You can specify also a saved model path. So
Absolutely, yeah. And
so that's how you can do a standard model save.
Exactly, yeah. In the API, yeah, you can specify either TFLite, save model, and I think there's a third one that I don't remember. Yeah,
I think there's a serving version as well.
Serving, yeah. I think there's 3 options here. I think it's somewhere here. Yeah, it's in this API here. Cool. So we export it to TFLite and then we re-import it. And we're going to do the evaluate on the test data. So notice when we had the TF version, it took about 39 seconds. Now it's taking almost 10 times, a bit more than that, to do the evaluation. The average precision didn't significantly drop. It was 53. Now it's 52. So we didn't lose a lot, which is good. This numbers upper class changed a little bit. For some reason, David got a little bit of a boost, and George and Robert dropped a tiny bit. So I went to 49 and 46 from 52 and 46. That was interesting. I don't know why, but not a huge difference that you'd say, okay, this is not going to run on an edge device. Cool. So that's the training part and the evaluation part. Then how do you predict? I added an option here. You can upload the model here because this took so long for me to train, right? So I had different versions of different models. I wanted to upload the latest model that I had. I had one from August, one from September. This is just some boilerplate code to basically take an image, pre-process it. This is using TFLite, right? So prepare the input and output tensors and run the actual object detection and draw results as well. You can also specify images from the web. I tried that as well. I have some images on the web. This is me. So you can also specify the threshold above which you want to detect images. So I pick my face here at 86% confidence. Then I wanted to do on random images on different sets, and this is the main results that we're going to share with you. So we're going to keep the detection threshold 0.3, and we're going to time how long it takes to do evaluation. And this is just a random image from, I think, the training set. No, from this list here, yeah. So I picked my face, even though I'm wearing sunglasses, and there's a lot of light in the background as 80%. Cool. So now what we'll do is we'll sample 6, 5 here, but actually I'm going to sample 6 in the next code. Images from the training, 6 from the validation, 6 from the test. I'm going to look at the results in Colab here. So this df query set equals train, validation, or test. This will change. I'm going to sample 6. I'm going to convert them to a list. That will be our list. And I'm just going to loop through that list and open that image, run it through our TFLite interpreter, run the object detection, print the name of the image, how long it took, and then the results. So you can see here, took about on average 9 seconds using the TFLite model, 9 seconds, almost 10 seconds. So these are results using the training sets, right? So let's take a look here. So this is pretty well defined. You can see the 3 of us. This is me. You can see my face. This is some profile it detected. This is the closest one. Did pretty well, 8861. It picked here both of us. If you see here, both me, the main frame, as well as Robert. Robert is 71. I cannot tell what I am. Then, yep, it picked the three of us as a screenshot from a YouTube video. This was the aspect ratio that I was telling you that it took me a while to figure out, but it was the width, the height ratio was so large that our model couldn't pre-process it. We're still in the training set. Another round on the training set. So on the training set, we expect to do really well, right? Because we were trained on it. Pick Robert here, even though he has a hat, sunglasses, 75%, 86 for me, 89. This threw me off. I think this is me. Maybe it's watched some of my YouTube videos and recognized my voice. I don't know. Yeah. It didn't pick anything on this end, which was labeled. I didn't label anything here. I labeled us here. Cool. The last training batch, me, picked Robert as well, 44 here. I noticed some images showed rotated, even though when I opened them on Google Drive, they were straightforward. So I don't know why. David from Profile with interesting light combo there. I like that, 68. The classic one from Robert. This would be a movie poster if you ask me. I like the colors here, 70%. 69 for me here, and then 70s and 80s for us here. Cool. Validation. This is images that the network was not trained on. So David, 60. This was a group photo that I took with some friends from church. I am here. Robert is not here, but for some reason the model thinks this is your Robert. This I'm surprised it picked all of us. Like I was really glad. So, because these are very small images, by the way. Okay, this is screenshot. So Robert says 50, David 70 something percent, George 69%. The wide ratio ones, I tried. No, now I know what's the issue. Now I'm hoping maybe for like if I had room for this, I would just make sure that this is rescaled to the proper ratio. This one, we're tiny here. It didn't pick anybody. Yep, you're here, Kathleen, too. And David, it picked you up. It didn't pick me up here. It picked us up here. Me and you, David. And last validation. This is sample, so you might see the same image more than once, FYI. This is me trying to look on the side, pick me up as well. Cool. Test. These are images that the model has never seen. Okay, I'm surprised how it picked me here. Like what? I'm wearing sunglasses and a face mask. I don't know. That was really good. I was surprised by that. Picked us here. A very contrastive here background. Picked us. Picked me as well. This is the aspect ratio issue. Picked you, David. So this is a good overall result, I think. Yeah, this is the only aspect ratio one, the weird one that was able to work. I don't know why, but for some reason this, I think this is from the aspect ratio one, was able to find you, Robert.
But that bounding box is interesting.
Yeah, that bounding box is crossing Zoom sessions and countries. I was in Greece here, you were in India. That's my mom's balcony. Yes, same image here. The last test. Okay, it didn't pick me here, good, because I don't think I annotated this. No, yeah, I didn't annotate this, so it didn't pick me.
It got the little ones above it.
It got the little ones. No, it got you and, oh, it got me, hold on. It got Robert as George. It got you right. And obviously me didn't pick up. And the most interesting is right here where it thinks it's me with 85%. And I think it's Robert doing the karate kick here with 34%. Love it. So I can tell that Robert knows martial arts just from this photo. Okay. So that was different batches from different sets. Yeah, I have the demo here for the app as well, but we showed that. So yeah, that's the main presentation that we had for you. We have a few links I'll go for real quick, but I'm gonna pause here for any questions or comments.
I had a question
Yeah.
in general about your training data.
Yeah.
So I know this is a proof of concept, and it looks like you had, I guess, how many images again for your training set? It was like 150 or something.
Yeah.
Okay. So I guess I don't know how many other projects you've done with data sets and using Colab. You know, I was just participating in this Kaggle competition for COVID object detection. And one of the headaches that I found encountering it was when I was trying to use the Google Drive and mounting the Google Drive and trying to gather and train on this giant data set of all these X-ray images.
Wow.
Basically I hit this wall where it basically barfs when it's trying to scoop up all this data and mount tons of gigabytes of data from the Google Drive. And I was just curious, have you guys ever encountered this? Have you found a good workaround? Because I use Google Colab because it's a cheap solution to trying to, you know, teach myself machine learning and deep learning projects. And I don't feel like I want to go pay for, you know, compute instances with giant, you know, disk space. So I was just curious if you guys had any experience with that, workarounds.
Yeah, I've run into that. It is an issue. You're gonna eventually, the connection between Google Drive and Colab can be
timeout.
It can have problems, right? So very large data sets. I've run into that many times. My only solution is to use GCP, right? So use their cloud. You know, when you go to Google's own cloud, it's fine. Then you run it. You have no problems. It's very, very seamless. Then you do have to pay for that. It's a small amount, but they do give you, when you first sign up, I think, George, maybe you remember, you get like quite a bit of credit for the first year or something.
$200,
yeah. So you can, if you don't you know, if you're efficient and don't go over $200 worth of cloud storage, you can do it for free. But
the storage is pretty cheap unless you have a real massive data set.
Yeah.
Well, yeah, I mean, this thing was 500
APIs
gigabytes.
are a little bit more expensive when you're calling numerous functions of theirs, but just to store data there is pretty cheap.
Yeah, so I mean, I don't mean to hijack your meeting here, but basically when I got into that, I tried doing that. I went that direction, and what happens is Google like did not allocate me a resource with a GPU. It was basically you had to start paying and becoming a paying customer in order to use the GPU. And maybe I'm doing something wrong, but that's the wall I hit. And then I got into this mess where I had this instance, I had to set up all this instance, but then now I'm paying for the instance when the data is at rest. Anyways, there was a lot of infrastructure stuff I had to teach myself, and it was kind of a pain. But yeah, anyways.
That's where, absolutely, cloud is another one. Another easier solution if you don't want to go with cloud is, even for my session here, this training 50 epochs. The free version of Colab has a 12-hour limit. I mean, I was not training for 12 hours, but the idleness. So it basically needs to make sure that there's a user behind this Colab and you're not using it for, you know, for your own business. That's, I think, the mentality behind it. But I had to upgrade to Colab Pro, which is like $10 a month, and you get faster GPUs, a little bit more memory, and longer runtime. So for me, I saw significance here based on jumping from the free version to the Pro version. As a Pro Plus, I haven't needed it yet, but
So what I did the Colab Pro, and so what I did was I copied the data from the because I copied it locally to the Colab instance, right? And then so I transfer over the 500 gigabytes, right? And then at some point the session does expire, but then what happens is I lost all that data when I wanted to go back to my project and work on it the next day, because the instance is a short-lived instance, and it's so I was playing this games. So I think at the end of the day, I think Google's in the business of trying to make money and trying to,
Yeah, I mean, if you
when you're
have
handling
such-
large data sets, it's,
you have
yeah.
such large data sets, yeah, absolutely, you need Google Cloud, yeah, or AWS. You need a permanent storage, permanent, EC2 or
Yeah,
cloud compute instances. Yeah,
all right.
cool. Just a few links I want to share with you before we wrap up. This is the average precision, the TF Hub that we mentioned. This is a step-by-step instruction on how to train the salad maker. Oh, one more thing. Let me go back to the presentation because I'm not done yet. So yeah, this is the results as we saw. You can look at this in the presentation as well. Just make sure you do present because I have animations here. Some performance metrics, some links that we saw. Have them here. I don't want to dive too much on the app, but there is the code. We made it available. I didn't have to do a lot of changes. I just did some UI changes to put our own images, our own custom logos and text, not logos, as well as where do I plug in my TFLite model on Android app. And I don't want to delay this session too much, but if anybody has any questions about that, I'm happy to answer them in the end. So yeah, regarding that, this starting point, the starting tutorial gives you a step-by-step process on how to download and how to edit, how to train, how to deploy, and how to use it on your phone for the salad version of it. This is the collab version of it. The paper, the COCO evaluation metrics. And then we had several loss functions, and I was looking at the code for object detection core losses. There's several of them, including this focal loss that we saw. So let's see. So there's a weighted L2 localization. There's localization losses based on where the boxes are located, and classification losses. Say this is George or David or Robert. And there's 3 under here and 4 under here, and they're defined here. If anybody wants to take a closer look. There's also
focal loss is really neat. It's you can, it's not the subject of our talk here, but it's very important for object detection and regarding backgrounds and how the background is downweighted. Yeah. So yeah, if anybody has any further interest in that, I encourage you to look that up. Yeah, there's a paper on it. Yeah.
Right. Okay, cool. Yep. This was an interesting blog for me as well, this detection. I think this is from a guy that works now at OpenAI. So he has a really good blog, a 4-part series. In the last one, he talks about 1 and 2 stage detectors. And I think he has specific applications or specific definitions of loss functions for the different. This is for YOLO or RetNanet, I think. So yeah, the pyramid loss function. Yeah. Then we used, and I'll show real quick here, makesense.ai, but there are many other services you could have used, right? You just get started and you drop your images here. It'll ask you to select the labels and then you just do the annotation. You can also use, I think Google AutoML has a labeling function as well. You can do it manually, or you can ask, you can pay, and it can have, let's say you have thousands of images, you don't want to do it on your own. You can have humans annotate them for you as well. That's a paid service for both cloud and Amazon Web Services. And I was looking at some quantization here, tutorials and steps, what exactly happens under the hood, and the actual conversion to TFLite. And some code for the app that was useful. Some other applications that I find useful is there's this pothole detection. Wouldn't that be cool if you can put it in your car and if your car has a front camera, it's like, oh, there's a pothole, slow down, or like, gives you a warning. I'm giving this as a preface for one of the upcoming projects that we're going to talk about. There's a face detection benchmark, but this is for face detection, not person detection like we did. But I like this because it has, I think, a collection of data for different scale. Like look at this, it's like so many people here, different poses, up, down, left, right, occlusion, expression, makeup, illumination. So there's no such set for ours. We had to make our own data set, but this was an interesting benchmark. And why we consider this is because we thought maybe we take a face detection model and we train it to recognize George, David, and Robert. But I think it would be a little bit, it's not as easy as it sounds, if I remember correctly. So we just went the custom way, approach where we annotate our own images, our own labels. Another approach would be this, where you take an existing model that does face detection and you just train it on new classes. Instead of just face, you say George, Robert, and David. I don't know how this would work, but it was an interesting data set for me. Cool, I'll go back to our page here. I'm gonna stop sharing. That's what we had for you, friends. We have a few other ideas and events coming up. We haven't finalized them yet, but they're coming up. We're hoping that one of them, Neil, right, will be able to share with us an awesome project that he and his team and you, Robert, have been working on. And we are hoping to have maybe Lawrence again. Yep, that'd be awesome if you can talk to us. We're gonna talk to him about the specialization, the school project we worked on, and some other things. We have some other ideas, so more is coming. And as always, if you have any ideas for what to pursue next, please let us know. Robert or Neil, did you want to say anything about your cool project, or should we leave it as a surprise for our audience? Surprise it is.
Hi, yeah, sorry, I just joined in a little bit late. I was like driving back from the airport for most of the talk. But yeah, I've been working closely with Robert and with some other folks. We actually entered something into a Hackster competition called the TinyML Vision Challenge, and I won't say too much about it. It uses machine vision, and it's related to bicycle safety. So we had a lot of fun building a real product that actually seems to work pretty well. So we'll be talking about that.
Cool. That's, I think, in a couple of weeks. So next week we don't have anything scheduled. Maybe we can do another happy hour. I'm happy to show you more about my trip. If you want to see some pictures from Albania and Greece, happy to do that. Or we can just take another break. Yeah, I'm open to ideas. Cool. That's all I had. I'll stop the recording here and I'll leave the session open if anybody wants to hang out. But again, thank you, friends, for being here tonight, and thank you everyone for joining us online. Hope you enjoyed it, and all the material, all the resources are on Meetup page, including the code for both Collab, the app, the presentation, and more.
Thanks, guys. I loved what you guys are doing. For the paper club we're meeting tomorrow, I put the link in the chat. We look at primary research about the things that we do with machine learning. So less of a how to and more of a why to. And we're going to look at optimizers tomorrow. So if you're, I'm not getting into the details, not getting into the math, more about what is each optimizer trying to do and how does it fail or succeed.
Awesome. Yeah,
very cool.
Awesome club. Yeah, we'll definitely be there. And so thank you for reminding us. Cool, friends. Okay, I'll stop the recording here, and YouTube guys and friends and also friends from around the world, we'll see you next time. For us on Zoom, I'll leave the session a bit longer if you want to chat.